Okay, uh, let's continue this lesson on circular motion. I believe the last time when we met in the lesson we spoke about the whole aspect of centripetal acceleration. And what that speaks to is the fact that whenever you have a particle that is moving within a circular path, circular motion, so to speak, right? We will have an acceleration that is directed towards the center of the motion. So if we were to consider this scenario here where you had some object being rotating in a vertical circle, what we would observe is that due to the fact that the velocity is changing with regards to time, then we can come up with an acceleration, and that acceleration is always directed towards the center, and as of such, we call it centripetal acceleration, right? So let's look at it to say that anything that is moving in a circle with a constant speed, right, then you will have a centripetal acceleration, providing that the velocity is changing, right, as it moves in its circular path. And that equation or that acceleration is given to us as v squared, where v is the linear velocity divided by r, which is the radius of the scenario, right? So we want to move along the line to talk about the whole aspect about forces, because what we have to understand is that once an object has an acceleration and it has a mass, then we can think about the object having some type of force, so to speak. Now it says according to Newton's second law of motion, the net force acting on an object is equal to its mass times its velocity. We know that for a fact, right? Now it says since in circular motion at constant speed, v, the magnitude of the centripetal acceleration is given as such, a is equal to v squared divided by r, as I would have stated earlier on. So once you have an object in circular motion, this is the acceleration of the object. So if that's the case, then by using Newton's second law that says force is equal to mass times acceleration, your force is now equal to mass times v squared divided by r. So this equation here is what would determine your force, right? And because we're using centripetal acceleration in this case, our net force, right, that is acting on the moving object is going to be what we call a centripetal force. Okay? There's another way we can write our net force, and that is when we say force is equal to mass times angular velocity squared times r. Remember that our acceleration can also be written as this. Our centripetal acceleration can also be written as omega squared times r. So since we can rewrite that to say that acceleration is equal to this as well from an omega standpoint, then we could have got this equation right here that says force is equal to omega mass times omega squared times r. But this is the more conventional one that we've used that says force is equal to mass times v squared upon r. Okay? Now it says when an object travels in a circle, as I would have stated, right, that the velocity is constantly changing. And once velocity is changing, then you have an acceleration. Now, mind you, since there is an acceleration, we know that there will be a centripetal force. It says here that the centripetal force is the net force which acts perpendicularly to the direction of the velocity towards the center. So at all times, once the thing is moving in a circular path, then you will have what we call centripetal force, which is your net forces that are acting towards the center of the circle. And we'll look at that from this standpoint. Let's imagine that you have a ball on a string, and you're rotating it in a vertical circle. Now, we can look at this diagram from different standpoints. Let's look at it when it's at A. Now, mind you that you have the ball being suspended, right, and on a piece of string. So you can expect that this is the ball right here. Now, we need to identify the different forces acting on the system when it is at this location. Now, at this location, we have the tension force, which we'll call Ft, right, which is acting upwards. Good? And then we have the weight of the object, which is acting directly downwards. So overall, we can look at Newton's second law to say that, let's look at the net force is acting. My net force in this case is going to be Ft, which is because it's going towards the center. So normally tension force acts along the line, or acts along the rope, so to speak, away from the object. So that's how the tension force normally acts, and it's going upward. So we say that's a positive tension force minus the weight. The minus is just to show that the weight is acting downwards. This is equal to our mass times acceleration. Since it's in circular motion, then it's going to be v squared divided by r. So at this very point, my net force that is acting on the system is given as such. However, even though that is my net force, that's not my centripetal force. The centripetal force in this case is going to be the force that is directing towards the center. So therefore, the tension force is the one that is directing or pointing towards the center. So all I would simply do is to just rewrite this to say that Ft is equal to mv squared divided by r plus mg. That will now determine and tell me what my centripetal force is. My centripetal force is caused by my tension force. So one of the things we must understand is that when we talk about centripetal force is no new type of force, right? It's just any forces that are acting towards the center, all right? When we look at when the object is at, or when the ball is at position B, at position B, I can highlight my forces. The forces that are acting at this point is your weight force acting directly downwards, that is equal to mg, and of course a tension force that is acting along the string, we call that Ft. Based on this scenario, right, our centripetal force is going to be given as Ft equal mv squared divided by r. Why we only have Ft is because that's the only force that is acting towards the center. Mind you as well that there is no acceleration along the vertical. The only acceleration that is taking place is along the horizontal, right, at this very point. So our mg right here does not have any impact on the whole centripetal force. At point A, we see where mg came into play, but at this very point, we're looking at the net forces. The net force is acting right here is towards the center, right, or along the horizontal is Ft, right? Only Ft, so we use that to say that Ft is equal to mv minus mv squared divided by r. Now when we move at point C, we can see that two forces are acting towards the center, right? You have the tension force, which is always acting this direction, and now based on where the object is located, your weight mg is also acting towards the center. So at this very point, we can see that we have two forces that are acting towards the center. So that tells us that my net forces, right, towards the center is going to be, and we're talking about when the object is at C, that is going to be Ft, right, plus mg is equal to mv squared divided by r. So at this very point, all of these forces that are acting here, right, acting towards the center, these are what is contributing towards my centripetal force. All right? This is what is contributing to my centripetal force. Now, one other thing that we can understand from this problem or from this question, if I were to make my tension force becomes the subject, if I make Ft becomes the subject, I then get a thing to say that mv squared divided by r minus mg. Now, what this shows me is that at the very top of the system, that is when my tension force is at its lowest capacity. Meaning that that's when it's at the lowest, the tension force at point C, at the very top, is very, very low, right? Because clearly we can see that our mg is being subtracted from mv squared divided by r. When we look at point A, we can see that our tension force, right, is much greater when it's at point A, because Ft in this case is equal to mv squared divided by r plus mg. So with that being said, it just kind of highlights to us that at the top of the system, right, my tension force is at its lowest in the system. And then now we can look at point B. At point B, similar to what happened, point D, I should say, similar to what happened at point B, it's the same thing that's going to happen at point D, where my centripetal force is just going to be Ft equal to mv squared divided by r, right? So that's just that from that standpoint. Now, when we look at it from a horizontal circle, right, a horizontal circle, we can see that the only force that is causing a centripetal force is going to be the tension in the string, right? So that's the only force that is acting towards the center when you have a string that is rotating an object in a horizontal circle, all right? So in this case, my tension force is just going to be Ft equals to mv squared divided by r. All right. Now, yes, there was I thought I had posted a thing here. Let me just check something. Not sure what is happening with that question. That question was supposed to be highlighted. Okay, here's the question. Yes. So here we have a question. All right, we'll soon go back to a few stuff. As a matter of fact, let me just go back and complete all of that and then come back to that question. So I should say that in understanding the whole aspect of centripetal forces, right? You know, a lot of centripetal, whenever objects are moving in any circular path, right, there is some type of centripetal force that is being provided. And when we look at a thing what we call a conical pendulum, right, then we'll understand too that the centripetal force can also be a component of another force, right, which will take us into another thing here, right? So let's look, just a simple definition as to what centripetal force is. It's just a force that is necessary to keep an object moving in a curved path, and that is directed towards the center of the rotation. So it's just a force that is just necessary to keep the object rotating in a circular path. You understand? That's what we mean by a centripetal force. So any force at all can actually be a centripetal force as long as it's keeping the object rotating or allowing it to continue to move in a circular path. Then that's what we consider to be a centripetal force. Now, as we talk about um, centripetal forces, we also want to talk about a pendulum because, you know, this type of pendulum, a conical pendulum, is going to involve some aspect of us understanding centripetal forces, right? And for us to come up with a formula, right, that we can use to find the period of a conical pendulum. And when we talk about the period of conical pendulum, we just mean the time that the pendulum takes to complete one complete oscillation, or we can say one complete rotation for the most part, right? Now, imagine that we have this is the equation, by the way. So here's an equation that we can use to find the period of of um of this conical pendulum, right? It says 2 pi times the square root of L, which L just signifies the length of the pendulum, cos theta divided by G, where G is the gravity constant, and theta is the angle that is formed between the conical pendulum and its suspension as it rotates. Now, what we want to do, we want to look at all the forces acting on the system. In a sense, with some questions, they say, you know, give us a free body diagram as to the forces acting on the system. Now, here is the system here. We have a thing rotating. We're taking a synopsis of it. Good? Now, my net forces, obviously, there will be a tension force acting along the line of the string. We call that Ft. Then, of course, because there's an object suspended at this end, we can classify we can identify the weight which is acting downwards. So mg acting downwards. Now, because the thing is moving in a circular path, there must be a centripetal force that is given in this scenario. Good? Now, the centripetal force is going to be a component of the tension force because the tension force is acting at an angle, right? Then we can resolve that tension force into its horizontal and vertical components. But one thing we must stop to think about first is that when we look at this entire system here, right, from the length of the string all the way to here, right, I am looking at a Z angle at this very point. But before I talk about the Z angles, let's just split this in its horizontal and vertical component. When I split it, I get a component on this side. Good. That's my vertical component. Then I would get a horizontal component which would look like this. Good. Now, with vectors tell me that I can shift this vector. I can shift this horizontal vector and put it down here. Good. So I can simply do that. Vectors allow me to do that. Now, we can ignore this for now. We don't need this for now because this is where my horizontal component is going to be. So I have now resolved the tension force into its horizontal and vertical component. Now, my question is, which one of these would provide a centripetal acceleration? Clearly, it would have to be the one pointing towards the center. So I can see that the one right here is the one that is going to provide a centripetal force. Good. But I now need to know what value does this have. In order for me to know that, right, let's look back at a thing what we call Z angles. So in mathematics, there's a thing what we call Z angles. And all it says is that whatsoever the angle the interior angles of the Z is, at this point, it's the same angle that's going to be produced here. So we have some interior angles in between this scenario, right? Where we can just simply say that whatsoever this angle is right here, it's the same angle that will be produced here. Similarly, if we look at this thing as such, if we look at this as a Z angle, right? Then it means that whatsoever the angle is here, that is going to be the angle on the outside right here. Now, mind you, seeing that we know that the angle is at this position, then we can now consider which side is my angle adjacent and opposite to. If my vector was still here, which is actually still there, but I just decided not to put it there because I want it to be here where I'm seeing it pointing towards the center, then my angle would be opposite to this side, which takes into account sine theta is equal to opposite over the hypotenuse. Now, because my angle is adjacent to the vertical side, then it means that I'm going to consider cos theta is equal to the adjacent divided by the hypotenuse. I want my adjacent to become the subject because I want to find that information. Now, my hypotenuse is equal to ft. So hypotenuse is equal to ft. I want to know what my adjacent is. ft. That's my hypotenuse. So just transpose this and I will get that ft cos theta is equal to my adjacent. So what it means now is that my adjacent side of this triangle here is going to be ft cos theta. Similarly, I want to know what the opposite side means. I now know that my hypotenuse is ft. ft times cos of theta will tell me my opposite. So it therefore means that the horizontal component is going to be ft sine theta. Now, since the acceleration is taking place along the horizontal axis, since that's the case, then what it means that there's no acceleration along the vertical axis. So what we're saying is that once the thing is in circular motion, our acceleration is directed towards the center. So it means that there's no acceleration along the vertical. So if there's no acceleration along the vertical, what it simply means to us, using Newton's second law, let's consider the net force is acting along the horizontal. I'm seeing ft cos theta that is acting upwards, and I'm seeing mg acting downwards. So if we were to look at Newton's second law, ft cos theta minus mg is equal to mass times acceleration. But remember we said a while ago that there's no acceleration along the horizontal. So along the vertical, I should say. So therefore, A is equal to 0. So in a sense, we're saying mass times 0, good, is equal to ft cos theta minus mg. If that's the case, if this is equal to 0, what it tells us is that ft cos theta is equal to mg. Right? Upward force equal to downward force once there is no acceleration. So we have equation 1 right here. Now, another equation that we can come up with is using Newton's second law again, looking at the net force is acting towards the center. What are my net forces acting towards the center? ft sine theta. And that is equal to my centripetal force, which is equal to mass times v squared divided by r. So I have another equation right here. Good? So I'm taking those two equations. And then I'm going to do something very fun. I want to get rid of ft. I want to get rid of ft. So I'm going to make ft becomes the subject. I'm going to make ft becomes the subject in that equation. If ft becomes the subject, it means that mg divided by cos theta. All right. If I now know what ft is equal to, which is mg divided by cos theta, I can substitute that in my second equation. So my second equation, if I substitute it, is going to be mg, and this is my second equation, mg cos theta times sine theta is equal to mv squared divided by r. So right here, where ft is in this equation, I am substituting that. It says, if you look at the note, it says let ft becomes the subject in equation 1, then substitute ft into equation 2. So I just did that a while ago, and I get that mg divided by cos theta times sine theta is equal to mv squared divided by r, which is what I have right here, right? Now, mind you, my m's can cancel out. So this m can cancel out this m. That's gone, leaving me with an equation that says g divided by cos theta sine theta is equal to v squared divided by r. Now I want to recall something from what I would have learned previously about the linear speed versus the angular, or the linear velocity versus the angular velocity. We have an equation that says, the linear speed is equal to the radius times omega, right? I want to substitute for v, right, in this equation. So if I were to substitute that, mind you that this is v squared. So since v is equal to r times omega, v squared is going to equal to r squared omega squared. So this is what I have now right here, to say that g divided by cos theta is equal to sine theta equal to r squared times omega squared divided by r. Now this r and this square is going to cancel out, leaving us with a nice equation that says g divided by cos theta sine theta is equal to omega squared times r. Now I want to do something else. I want to go back to my diagram right here. Now remember that r is the radius of the circular path, which, if we're considering it from where the object is, right, to the center, then this would signify what r is. So my r value is going to be right here. Mind you, this is the height of the system. This is the length of the system. Now I can consider using the whole trigonometry ratio, because all of this would have particularly formed a right angle triangle, which means that I can easily identify this side of my triangle using the whole concept of trig ratios. Since I have an angle right here, and this angle is opposite to my radius, the length of my radius, then it means that using this equation, sine theta is really equal to r divided by L. Remember, L would be your hypotenuse. So we're treating the sides as vectors. We're treating r as a vector. We're treating L as a vector and h as a vector. So looking at that, we get an equation that says sine theta is equal to r divided by L. I want to make r become the subject. When r becomes the subject, I get sine theta when r becomes the subject, we get that r is equal to sine theta times L. So let's take that r and substitute it in my lovely equation here. When I make that substitution, I now have g divided by cos theta sine theta is equal to sine theta times L times omega squared. Now I'm seeing sine theta on this side of the equation, and I'm also seeing sine theta on this side. So it can cancel out. So sine theta cancel out sine theta, leaving us with g divided by cos theta equal to L omega squared. So we're at this location now. We did say that sine theta cancels out. Now let's recall something again. Seeing that we're talking about circular motion and everything, this equation can come into play. That says our angular velocity is equal to 2 pi radians divided by t. Okay? Having that information, we can now make a substitution right here in the equation. So since this is omega squared, then omega squared is really equal to 4 pi squared divided by t squared. So we're substituting omega squared in our equation, right? So we therefore have g divided by cos theta. We studied that this gone already. So what we're really left with is, let me write it right here. So g divided by cos theta is equal to L times 4 pi squared divided by g. Well, my bad, not g, divided by t squared. Divided by t squared. Divided by t squared. If we make t squared become the subject, right, we can get t squared to be equal to L times cos theta, right, times 4 pi squared divided by g. And if we make t become the subject, we would end up with this lovely equation. You know, to make t become the subject, you just find the square root of both sides, right, which is quite simple, right? Because you want t, and t is being squared, so you find the square root of it, and you end up with this equation that says that the period of a conical pendulum is really given to us as 2 pi times the square root of L cos theta divided by g. So very important equation to us because we're dealing with circular motion. So we from time to time will use that to find out certain information. Wonderful. And with that being said, it takes us into a simple question where we are being asked to draw a free body diagram that shows the forces acting on a pendulum bob. Also, it says calculate the tension in the string. Following that, it says the period of the motion. So here we have a question, and we want to go ahead and do that. The length of the pendulum has been given to us as 1 meter, and the mass has been also given to us. Okay. Also, we know the angle. We know the angle as well, which is 40 degrees. Okay. So let's see if we can go ahead and take on this question. All right. So let's proceed now. So first we want to identify our forces. So seeing that the mass is located here, we know that we're going to have the weight acting down, right? We know that we have a wire here, so it's going to be a tension force, Ft. Now we can split the tension force in its horizontal and vertical component, right? This is going to be based on where the angle is located. It's going to be Ft cos theta. Then we have a force acting like this, which is the horizontal component Ft sine theta. That's what will provide our centripetal force. That being said, we have completed the diagram. All right. Now we want to find the tension in the string. Remember, if you can remember, we said that we did say that when we look at the vertical aspect of the forces, right? We said that Ft cos theta is going to equal to mg, providing that we know the rest of information, right? We can transpose to make Ft become the subject. So mg divided by Ft, my mass is 400 grams, so that's going to be 0.4 times 9.8 divided by cos of 40 degrees, right? So let's just see if we can calculate that quickly. Good. So in this case, I'm seeing where my Ft is going to equal to 5.1 newtons. That's my tension force. Now it wants us to find the period, right, of the motion. We just derived the equation for period that says C is equal to 2 pi times the square root of L cos theta divided by G. So we could essentially put in the values for this. So 2 pi times the square root of L, which is 1 meter, times cos of 40 divided by 9.8. When I found the square root of that number, I get this. Then we'll just multiply it by 2 pi. Let me just check something. Let me just check some. Alright, yeah, this is when I square root it, everything underneath here, I get this value. Okay, so let me just check it again. Cos of 40 divided by 9.8, square root that. Yeah, so that now multiplied by 2 pi gives us an answer to say that the period t is equal to 1.75 seconds. Alright, so that completes that. Now, what if we have a scenario where we take a bucket of water, right, and we wheel it around in the air? Good. So if we have a circular bucket or a cylindrical bucket containing water, and that is wheeled in a vertical circle, it says draw a free body diagram showing the force acting on the system, right? Draw a free body diagram. Yes. Yeah. So in a sense, this is what you would have in terms of drawing that free body diagram. Now, mind you, there's no tension force in this case, right? But the centripetal force that will be provided is going to be your normal reaction force. So because you have the water inside of the bucket, right? Clearly your weight is acting down, mg, and then now because of that weight that is acting down, or the water that is acting down on the bottom of the bucket, then that bucket is going to produce a normal reaction force. All right? Normal reaction force. So, in this case, at the very bottom of the system, then that's what the overall forces are. We could find our net force at the bottom to say that Fn minus mg is equal to mv squared divided by r. Okay? mv squared divided by r. And clearly, at the very bottom of the system, that's when your normal reaction force would be the greatest. Okay? At the top of the system, right? Since the weight is acting down, good, your normal reaction force would presumably acting down as well. Good. But in essence, your normal reaction force should be acting up, but in this case, it's acting down. So in essence, our net force is acting down would be Fn plus mg. Okay? It says, what is the minimum constant speed at which the um, the cylindrical bucket of water must be wheeled in a vertical circle of radius r so that the water does not fall out when the bucket is upside down at the top of the motion. So at the top of the motion, we said that there are two forces. Um, so this is what we're saying here. At this very point, right? There is no normal reaction force really at this point. But let's just write this out to say that Fn plus mg is equal to mv squared. Now, at minimum constant speed, right, we wouldn't have any normal reaction force in the system. Okay? So in essence, the overall force that is acting down or towards the center is going to be mg. Okay? Right? So in this case, we're saying that mg is equal to mv squared divided by r. So we could cancel out this, cancel out the m's. We want to find this minimum speed. So in essence, we're just coming up with an equation, right? So we can say v squared is equal to g times r. We want to find v, so in essence, we're saying that v is equal to the square root of g times r. So this would tell me the minimum speed that will be required for us to spin the bucket at the top, right, so that the water doesn't fall out. Okay, so that would be the minimum speed that the bucket must be going at so that the water doesn't fall out. It says, what is the nature of the force that must be present at the lowest point of the motion in order for circular motion to take place? So this is what we're talking about. The nature of the force is going to be the normal reaction force. So that is the force that will be present at the bottom of the system that is causing a circular motion per se, right? Because that's the force that is acting towards the center. It says, what is the magnitude of that force? The magnitude of that force, Fn, is going to be given as mv squared divided by r plus mg. All right? let's talk a little bit more about the normal thing here, normal reaction force at this point. It says, so at the top, we can clearly see that this is the net force acting on the system, right? It says where the normal reaction force provided at the bottom of the bucket, it says the net force um, at the top must be minimal in order to in order for minimum speed to be achieved. So F normal reaction force must be equal to zero. So the normal reaction force must be at minimum since we're trying to find the minimum speed of the entire system. So this gives us this equation. And then obviously we said that the speed of the system is given as such, right? So that's the minimum speed. And I must say this, that quite often they will ask you what is the minimum speed at which the system must be going at for it to continue in circular motion. Then to find the minimum speed, you have to consider when the object is at the top or at the center, not the center, but at the very top of the system. So like at point B, that would be when you should consider what is your minimum speed, or what would be the speed that you need to have in order for you to continue moving in a circular motion. All right. Now let's look at this question. It says here that a ball of mass, um, a ball of mass 64 grams connected to a string is wheeled in a vertical circle of radius 30 centimeters, and it says with gradually increasing speed. It says discuss the motion at low speed. So at low speed, what they really want us to do here is to just look at what is happening for each cases, or each portion of the motion. So at this point, at point A, we would expect, so we can say at A, right, the system, or the net force is acting on the system is going to be Ft, right, minus mg, and that is equal to mass times v squared upon r. Now at point B, that is given to us as Ft is equal to mv squared divided by r, and at point C, right, we can clearly see that Ft plus mg is equal to mv squared divided by r, and at point D, similar to what happens at point B, then your tension force or your centripetal force is given to you as such. Now it says if the maximum strength or tension of the wire or the string is 3.4 newtons, it says where and at what speed is the string most likely to break. Now, if you can remember, we said that at the bottom here, that's when you would have maximum tension in the wire, or maximum tension in the string. So the tension that they're talking about that is maximum is located at this point, which is 3.4 newtons. Good? If that's the case, if this is what the tension force is at that point, then the equation that we must consider to find the speed at that point is this one, is when we're at point A. So at A, right, Ft is equal to 3.4 newtons. So we can pretty much put the equation together that says Ft is equal to mv squared divided by r plus mg, right? So having said this, we can definitely put in the values that we know and try to find v squared, or try to find v. So you could go ahead and put in those values. At this point, my equation or my answer should be um, 3.4, 3.61 meters per second squared. Because when you put in the mass and the radius and everything, all of these things must be in SI units. So SI units mean the standard international units, right? So for mass, that is obviously in kilograms. So let me just work out the first portion that you guys need to. So provided that I know my tension, which is 3.4, that is equal to the mass, which is 0.064 kilograms, dividing that by the radius, which is 0.3. Well, yes, radius. Let me check. Were we given the radius? Yes, the radius was 30 centimeters. So in essence, in that in meters is 0.3, and we're timesing that by v squared plus the mass times g, which is 0.064 times 9.8. So you should get something to say that v squared is equal to 0.34 minus 0.625 divided by 0.213. So in essence, that's how we get that v is equal to 3.61 meters per second squared. The question goes on. So we know the speed now, and I must let you note this thing, guys, right? Remember, at different locations, when the object is here at point B, the velocity of that object is really pointing like this. So that would be my velocity at point B. When the object is at point A, my velocity is tangential to my circle. So that's the direction of my velocity. So clearly, when we move on to this question, right, that says, where will the ball land after the string breaks if at the point of breakage of the string the ball was 40 centimeters above the ground. Guys, the tendency of the string will break when the tension is much stronger. So that's something you must also think about, right? So in essence, we're saying that the string will tend to break where the tension force is the greatest. So at point A, you would expect that that's where the string could possibly break. It will be harder for it to break at this point because you have less tension force acting on the system. Remember, our tension force at point A is a combination of the centripetal force, mass times v squared over times r, divided by r, plus mg. So that's where your tension force is maximum. Good? So with that being said, we want to find where will it land when it breaks. So in essence, we're trying to find the distance that it traveled along the horizontal. It pointed out to tell us that the breakage took place 40 centimeters above the ground, right, which is our y value in this case. So in essence, coming from where the object is to where it is landing, that's going to be negative 40 centimeters if we're looking at a displacement type of scenario, because y is really a displacement, right? So let me just make some space right here. Good, for us to answer that question, right? So in essence, we're saying that we want to find the distance. Before we can find that distance, we need to know the time that it takes for the object to fall. So we need time, okay? So in order for us to do this, we must consider this equation that says my change in displacement equals to initial, or my velocity along the vertical times the time plus a half at squared. So this is one of the equations of motion that we would have derived earlier on back then, right? That we would generally use in projectile motions and all of that. So imagine, in essence, this is a projectile motion question. We identified that our overall change in displacement is going to be negative 40 meters, and because the object at this point is moving, the velocity of that object is purely horizontal, what it tells us is that there is no initial vertical velocity. So our Vy naught is going to be equal to 0 plus a half at squared. A in this case is going to be our acceleration due to gravity, which is given to us as negative 9.8, and then t times that by t squared. So at this point, we have an equation that says, as a matter of fact, this is not 40 meters, it's 40 centimeters, so that is equal to 0.4 meters, and that is equal to negative 0.4 meters, right? And then that is equal to negative a half 9.8, which is going to give us, right, we could work that out to say that 4.9 t squared. We want to make t squared become the subject. So if we make t squared become the subject, we could literally find t, which is your time, to be 0.286 seconds. Okay? Having said all of this, because we want to find the horizontal distance, whenever we are dealing with the horizontal motion, right, along the horizontal, there is only one equation that, well, yeah, pretty much one equation that really helps us, and that is using the regular velocity equation that says v of x is equal to the displacement along the x divided by time. We want to find the change in displacement along the x-axis. So in essence, we're saying that v of x times t is equal to my change in x, or my change in my displacement along the x-axis. Now, we know the horizontal velocity. The horizontal velocity will not change in the entire motion. The reason why the horizontal velocity will not change is because there is no gravity acting along the horizontal. All right, so that will remain constant throughout the experiment, or throughout the whole duration of the thing. So because at this point where the object broke, the horizontal velocity, which is this thing here, we found that to be 3.61 meters per second. So that is the same velocity that the object will have when it reaches here. So taking that value, 3.61 times the time, which is 0.286 seconds, that will determine and tell us the distance where the thing will land. And we'll do all of this math. It kind of shows that the distance is going to be 1 meter. So in essence, it's 1 meter away that the object has fallen. Okay? So that's what that covers that. Another thing we should talk about is when we have cars. So this is back to centripetal forces. Now, static friction force can also provide a centripetal force. Whenever we have a car moving around a roundabout or turning any corner, right, there will be a static friction force that is acting towards the center. So let's imagine that static friction is coming as a result of the contact with the wheel and the surface. And we're seeing where that is acting, that is pointing towards this way. which is pretty much towards the center. So if we were using that same car, then we would expect that the centripetal force will be acting like this. So what we're really saying is that it says in order for a car, right, to travel around a roundabout without skidding, good, or sliding, right, the car must be going at a certain speed, which we call the maximum safe speed. So any car moving around in a roundabout, right, for that car to remain, or we should say, should travel in that roundabout um without sliding, right? It must be traveling at a maximum safe speed. And it says that this can be found by the static frictional force, because it's a static frictional force that will prevent the car from sliding. Because remember, frictional force is an opposing force. So that is the force that is preventing the car from sliding when it is moving in a circle. So if that's the case, what it tells us is that the centripetal force, the force that is keeping the car in motion in a circular path, is really the static frictional force. So we say we can recall that static frictional force is related to the normal contact force, right? So if you remember when we were looking at the whole outward machines and all of those things, right? And kinetic friction and all of that, right? Then you can remember that there's a relationship that exists with static friction force and the normal force, which tells us that the static friction force is directly proportional to the normal reaction force. So the more normal reaction force you have is the more static frictional force you have. So this is what we're saying. We're saying F, or static friction force, right? Static friction force, we're going to call it F stat, right? That is equal to mu S, which just speaks to the coefficient of friction times the normal reaction force. Now it says that since on the horizontal surface the normal reaction force is equal to the weight resting on the surface, we could essentially say that our normal, let me just write this. So F stat, which is your static frictional force, is equal to mu S times mg, right? So if we were to consider the overall centripetal force, then we're really saying that mu S times mg is equal to mv squared divided by r, right? And we can use this equation to find the maximum safe speed, right, at which the car must be going, right, at, so, to prevent it from sliding, where we're saying that v is equal to the square root of mu s times r times g. So from this equation, we can identify something, that it tells us that the safe speed is really dependent on the radius of the roundabout, or the radius of the circular motion, right? And also it also depends on the coefficient, the static coefficient, or the coefficient of static friction. So if your coefficient of static friction is relatively low, then that will tell you that to keep the car from without sliding, then the overall force must be, or the overall velocity is going to be relatively low to keep it, so to speak. All right. Another thing that we should talk about is whenever we have a car being banked on a road. I don't mean banked on a road is like you driving up on the banking. Now there are some car racing um, thing that allows you to can drive along the banking of the track, right? Also, I don't know if you have ever been to the national stadium, right? And you would have observed some type of road or traveling path along the stadium section. When you think about those bicycle riders as well that generally ride along this part of the track, right? Then what we can observe is that when you have those persons riding like that, there is a centripetal force that is keeping them in line. So in essence, there's a centripetal force that is always keeping them moving in that circular path, because remember your centripetal force is a force that will always want you to continue to move in a circle. Good. We must be able to can identify that centripetal force. What is really causing that centripetal force? Here we're going to look at it. So let's imagine that here you have the car, right? We have a car that has some type of mass. So imagine that this is your car and you're driving it along a banking. Clearly, your weight force is acting downwards. So mg is acting downwards like that. Now, with any object that is in contact with a surface, there will be a normal reaction force. So your normal reaction force is going to be perpendicularly to the surface of the that the car is on, right? So that's my normal reaction force. So if I were to go ahead and split that normal force into its horizontal and vertical component, if I were to go ahead and split that into its horizontal component, so this is your normal reaction force. So we can call it Fn, and this is mg right here. Then by considering the components of it, right? This is going to be the y component, providing that the angle is here. Then this side is going to be Fn Fn cos theta. Then the next component is obviously going to be directed like this, right? So Fnx is pointing that way, and in this case Fnx is really equal to Fn sine theta. So what we're really saying that when a car is being banked, right, you can find the centripetal force by using Fn sine theta, or the centripetal force is really equal to Fn sine theta. So that normal reaction force, a component of it, the horizontal component, is what is contributing to the centripetal force. And that is the force that is keeping the car moving in the circle. Okay? And here we have some information that you can just read for yourself. All right? Imagine that we have a question that says a cyclist is traveling around a bend, right? With a radius of 15 meters on a horizontal road. It says that the frictional force is related to the normal reaction force from the ground, and the coefficient of friction may be the coefficient of friction is given to us by that equation that says F is equal to mu times R, where mu is the coefficient of friction and R is the reaction force. It says in dry conditions, mu is equal to 0.5. It says calculate the maximum speed at which the cyclist, right, can travel if he is not to fall off. So in a sense, we're trying to find the maximum safe speed. So you have a cyclist that is moving around here. So let's imagine that you have a bicycle, right? And you have a cyclist on the bicycle, right? You have a cyclist somewhere here. I don't know how to ride a bike. So he's going this way, right? And he's going around some some bend that has a radius of, you know, 15 meters. Good. We're saying that there's a centripetal force, and that centripetal force that is causing him to move in this case is the frictional force. So we just highlighted a while ago that F, which is our frictional force, is equal to mu times R, right? So we could write this to say that um, since we know that the frictional force F stat is equal to mv squared divided by R, and we have highlighted what F stat is, which is mu times R, right? That is equal to mv squared divided by R. R is also equal to m times g, because along the horizontal, right, the normal reaction force is equal to the weight. So mu times mg is equal to mv squared divided by R. We can cancel out m's. By canceling out m's, we could transpose to make v squared become the subject. So v squared is going to equal to mu naught times R times g, right? V is equal to the square root of mu naught, well, mu times R times g. So in a sense, if we go ahead and put in the values, that says V is equal to square root of 0.5 times 15 times 9.8, then you will find the maximum speed at which, right, at which the vehicle or the bicycle should be going at. So this gives us a value that says V is equal to 8.57 meters per second. So that would complete this aspect of the course, talking about circular motion, right? So please ensure that you understand all of what we have gone through here, right? So that's about it for this lesson.